Loud. Amazing. All right, thank you, everyone. We're here with Ian and the Vulcanize team to hear about what they put together with Vulcanize. Lots of stuff with IPFS, IPLD, and how that can help in storing and distributing blockchain state. So Ian, go ahead and take it away.
Thanks, Boris. Appreciate it. Yeah, my name is Ian Norden. I'm working with Vulcanize. Been working with Vulcanize for about 5 years now. And so the stuff that I'll be going over today is kind of the culmination of everything that I've been working on for the past 4 or 5 years or so. And so I'm going to go ahead and just share my screen here. And can everybody see that?
Yes.
Perfect. And I'm going to drop this HackMD link in the chat as well. If I can find where the chat went. This will just serve as like something that you can come back to if you're interested in revisiting some of the stuff that I'm about to go over. Don't seem to be able to actually link anything in the chat. Okay, I won't worry about that for now. But I'll link this in the Filecoin Slack after we're done with this talk. And so, yeah, essentially what I'd like to go through here is the stack that we've developed from the bottom up. And so where I'll start is with our state diffing Geth client. And so this is a custom Geth client that we've been working on for a while. And the purpose of this client is to enable us to index the entire Ethereum state data as IPLD objects. And so to do that, we generate state diff objects, which are composed of only the state and storage nodes, which have been updated in a given block. And then we write these out to Postgres. And while we're writing them out to Postgres, we also generate additional secondary indexes and maintain the relational mappings of all these objects to one another. And originally we had done this as a sort of a disjointed process using this IPLD ETH indexer codebase. But what we realized pretty quickly is that that's too much of a performance hit to be feasible because it required us to basically iterate these state objects twice instead of once. And so instead now, while we're actually iterating over the state tree using this difference iterator, we write those nodes out into a Postgres transaction while we're doing that iteration so that we don't have to reiterate the object at a later time. So this repo, the IPLD ETH indexer repo, is somewhat useful from like a documentation perspective because it helps expose what we're doing, but it's actually no longer used in our production stack. Instead, we're indexing the data directly from our modified Go Ethereum client. And another thing I should mention perhaps is, well, I'll just go ahead and jump here to the database schemas. Hopefully this is viewable. So this is just a mapping of our database schemas. And so, at the root of all this is a single table, the Postgres IPLD blockstore, which is just obviously a mapping between a key, which is the blockstore prefixed multi-hash derived key, and the data, which is the actual binary IPLD block. And so then we have all these additional Postgres tables shown here. I don't think I can really give like a complete comprehensive view.
Are you okay with questions along the way?
Oh yeah, absolutely.
So the key and the block store, if I'm understanding correctly, that key is actually a SID of a block?
It's not quite a SID. It's so I can't remember in what version the update occurred, but at some point it was changed. The block store was changed from using a CID for the key to using the multi-hash, so that you could. So instead of being a CID, it's actually just a block store prefix multi-hash.
Great, thank you. But essentially, this is using Postgres as a block store for an IPFS node.
Exactly, and we actually have a branch of Go IPFS that can use this Postgres table as the backing block store. I need to take the time to like rebase that on the latest release of Go IPFS and try to upstream that. But there's a link to that as well, and that hackmd that I'll follow up with. But yeah, you can actually use this Postgres table as the backing block store for an IPFS client.
Awesome, thank you.
And yeah, so you have this table which holds all of the IPLD data, and then you have all these additional Postgres tables which provide additional indexes and relational information about these different Ethereum objects. So, at the top of it all is the header CIDs table, and then you have transactions and uncles, and state CIDs which link back up to the header. Transaction CIDs will, by foreign keys. So these transaction CIDs, uncle CIDs, and state CIDs table contain a header ID foreign key to reference back to the top level header table. And then, the receipt CIDs then reference up to the transaction CIDs, and the state accounts and the storage CIDs reference up to the appropriate state CIDs entry. And so this all rolls up to the header. And of course, each of these tables themselves retain a direct reference to the blocks entry that contains the IPLD data for that specific Ethereum object.
Bottom line, a real-time store of Ethereum state, which, because it's in Postgres, can be queried very simply and easily, but also stored as IPFS, IPLD blocks. So they're self-verifying and kind of known good.
Exactly. Yeah, so it allows us to basically, expose this data using the conventional IPFS interfaces, but then we can also expose it using the conventional ETH-JSON RPC interfaces or our own unique interfaces that leverage the secondary indexes or relational mappings that don't exist in IPFS or in level DB. For the Ethereum data is usually stored in a level DB database. And actually, I'll just go ahead and give like a peek into our production database to kind of give like a sense of the scale of this. So this is just looking at the ETH table. So we have the IPLD data in our public schema, and then we have separate schemas for different blockchain data. So here for Ethereum, we can see the number of entries that we have for these different tables. And you can see, state CIDs, storage CIDs are in the billions. And in general, oops. Yeah, so currently in our production database, we have about IPLDs in that Postgres table that are being indexed using these Ethereum specific tables. And so as just mentioned, the nice thing about the way that we're indexing the data here is that we can expose the data using Go IPFS, but we can also expose the data using conventional ETH-JSON RPC endpoints. That's what we do with this repository, the IPLD ETH server repository. So this builds up all of the, it supports all of the ETH namespace JSON RPC endpoints, which is the namespace used for querying all data. There's other namespaces like net and admin, which are used for other node operations, which you can't really recapitulate on top of just the raw data. You need additional node information. So we aren't able to support all of those, but we're all able to support all of the data querying endpoints. And so this exposes an exact replica of that interface, so you can actually interface it with this Postgres database in the same capacity that you could a normal GEF client through that JSON RPC interface. And it also, as I said, exposes unique endpoints. We use PostgreSQL to do that, which can leverage some of these rows that don't exist otherwise. And this database uses this package here, IPFS ETHDB, which is a recapitulation of the low-level Geth ETHDB interface, which is the lowest level interface for an underlying database through Go Ethereum. Usually it operates on top of level DB. And so this is allowing us to operate that on top of our Postgres database. And so using this, you can build up essentially all of the state machinery that you have in the Go Ethereum client. And so it's actually theoretically possible to write a Go Ethereum client that actually uses this database as its primary data store. Although there's some performance reasons why you might not want to do that. But yeah, so using this package, you can, for example, create a tree database or a state database. And these are the low-level types which are used to perform pretty much all of the state operations in Go Ethereum. And so we're leveraging that here in the IPLD ETH server to instantiate an EVM on top of the ETH IPLD data. So then you can perform any type of EVM operation on top of the ETH IPLD data. For example, you could do ETH call on top of this IPLD data. And so that's one of the more powerful things about this is just the way that it's able to, one of the more powerful things about this database is the way that it can actually plug into all these other systems, IPFS, the Go Ethereum stack, and then of course like our own functionality as well.
What would you use that EVM functionality for? Can you give an example?
Yeah, primarily we use it for supporting ETH call. And ETH call is one of the ETH JSON RPC ETH namespace endpoints, which allows you to basically execute arbitrary transactions on top of arbitrary block state. So you provide a block height and you provide a message or a transaction, and it executes that transaction on top of that state and returns some result. It doesn't actually, it doesn't persist that state to the blockchain. It just executes it locally and then returns the result. So you can mock call different contracts or read state from anywhere on the blockchain, for example.
Right.
So this is sort of the base layer caching layer, the base level caching layer that we have. This this database that we have, and then we're able to expose these base layer interfaces on top of it. And then the next step in the data pipeline is consuming this ETH IPLD data and performing additional transformations on it, and indexing it in some additional capacity that's useful for some more specific application. And so we have a number of tools that do that. Namely the Watcher TS here, which is a set of packages that let you write what we call watchers, which are programs which watch this data, consume it, and perform some additional transformation on it, and then cache it in some secondary cache. So they create their own Postgres tables for the transformed ETH IPLD data, and cache the result of that transformation in those new tables. Oops, didn't mean to click that. And one example of how we can leverage this is here, the IPLD block explorer, which uses the base layer caching and generates some secondary caching to create a generic block explorer for Ethereum data. And the demo that I'm actually going to walk through today is here, the ERC20 watcher. And so this is basically just a Docker compose, which compiles all these things that I just talked about together into a single set of Docker containers and runs them so that we can demonstrate the functionality in a simple capacity. And so I've already built this image and deployed a test contract here. Just some random token guild. So we get, after deploying the contract, we get the address, and I'm just exporting that contract address and exporting my test MetaMask address here. And you can see I've already added this token to MetaMask, and currently there's no balance present. But what we can do real quick, is perform a transfer within this test environment. And this is just showing some log output from this process. And you'll have to excuse me, the computer that I'm working on right now is not particularly powerful, so there's a bit of delay here. And so these Docker containers also expose the IPLD ETH server GraphQL endpoints, and so we'll be able to interface with the data that we're indexing through this GraphQL, this local GraphQL server. Doesn't usually take this long.
The demo gods.
Probably Zoom stealing all your processor cycle.
Yeah, that would explain it.
This has happened to me before.
So basically what we're doing here is we're realizing that normally to do this, you would have to have a full node running. And these types of transactions are very hard to get. Say I want to get all of the transactions related to my personal address, or all the transactions related to a specific ERC20 token. Those are quite intensive to query.
Correct. Yeah. Because of the unique, because of these unique tables that we have that index it in a capacity that's not normally present on the level DB data. Sorry. You can, for example, do a database query which searches for receipts based on some specific block number, some specific transaction destination, and some specific topic or contract address. Or you can search for a specific state or storage node using, for example, the path, which is not usually possible. So you could query all the nodes along a certain path down to a certain leaf node, which would allow you to construct the proof much quicker than you normally would be able to. The way that it normally works is, you have an address that you want to get the balance for and prove the balance of that address. And so the path to that leaf node. The path is the hash of that address. But to collect all the nodes along that path down from the state root, for example, you have to iterate all the way down from that root to that leaf node. And that requires, on average, probably 6 to 12 database lookups, separate database lookups. So you end up spending a lot of time doing these database lookups, whereas in this format, you could perform that operation in a single database query and find all of those nodes along that path in a single query and generate a proof much quicker than you would normally be able to.
And because of the IPFS and IPLD structures, we can cache that query and in fact, potentially just return that same query.
Right, you could even write like a selector for that query. You could write a single selector which describes all of the nodes from a certain root hash down to some other tree node, some child tree node that you want to prove. And then you could actually take that selector and query, a conventional Go IPFS node if we assume that it has the data, which it probably doesn't. And then you would be able to you'd be able to get that data from there. And so you could verify that proof from some other source in a capacity that would otherwise be quite difficult. Okay, looks like that worked. Oh, so yeah, you can see I sent 100 units of gold and there's 18 decimals here, so it barely shows up. But the balance here has been updated. And I'm going to, whoops. Just show you that this balance was, what's it doing? 0 at the last block. And now at the latest block, we should have a value of, oh no, that's not the right block. That isn't the right block. Oh, I guess it's not the right block. Oh, sorry, I'm querying the, oh no, that's the right one. Let me fetch the latest block hash real quick. Real quick is a bit of an exaggeration. Is that not it? Oh, that's quite odd. You can see the balance is updated here in MetaMask, but for some reason it's not reflecting it in GraphQL currently.
It's caching, naming, or DNS. Those are the only options.
What are the uncles?
So the uncles are headers without any other data associated with them, that are they're blocks that were mined by some other miner who didn't happen to submit theirs in time to make them the canonical block at that block height.
Okay.
So in Bitcoin, they're not included in the blockchain, but in Ethereum they are, and they actually serve as an additional contribution to the consensus weight. Like in Bitcoin, we think of, the canonical chain is the longest one, whereas in Ethereum, it's more so like the heaviest one, where it's not just how long it is, but it's also how many uncles it has hanging off the edge as well. So yeah, they're just regular block headers that have all the normal block header fields, but they don't have a set of transactions or other uncles associated with them. And in Ethereum, they're limited to 2 uncles per block.
Gotcha.
And miners are rewarded a little bit for including those as well as the normal block.
One of the reasons that you want all of this data in a database, Brian, is that people who are performing analysis on consensus and block production and so on will want that uncle data as well. There's various things like network interconnectedness and other stuff like that and various other things that affect uncle production, and you're going to want to run queries and graphs and reports on that. So you want all of it in the same database.
Gotcha. Makes sense.
Let me try restarting the server. Apologies. Oh, wow. Okay. Huh. Yeah, I'm really not quite sure why it's not showing up. So we can see it in MetaMask, but for some reason it's not being exposed in GraphQL. And of course, this worked just momentarily before we started the call.
It's too small a value.
Of course.
Let's see if I can get the event at least. And I'm just actually just going to go ahead and do another transfer. But one thing that I can talk about while we're waiting for this is some of the other work that we've been doing, like on the actual codec work for IPLD. So we've been working with IPLD to do the implementations, the Go and TypeScript implementations of the new Ethereum IPLD codecs that work with the Go IPLD Prime suite of tools. And so most of that work is contained here in this repository. And so, yeah, we've rewritten and written all of the different IPLD codecs that we need for all these different Ethereum objects to work with the Go IPLD node interfaces. And this is actually complete now. There's some additional work that needs to be done. Right now we could use this with the basic Go IPLD Prime node interface, but we want to implement our own custom node interface that is a little bit more performant, doesn't have to use as much reflection, for example, as the basic ones have to. So we are going to write our own Go IPLD Prime node interface specific to these Ethereum types. So that's sort of the next step for this scope of work. And we've also been working on the analogous work for basically the work that's analogous to everything that I've covered so far for Tendermint and Cosmos. An example of that would be here, the Go codec.cosmos, which are the IPLD codecs, the Go IPLD codecs for the Tendermint and Cosmos data structure types. And we've also been working closely with the Cosmos teams within the SDK, the Cosmos SDK, to introduce features analogous to the features that we have with the state diffing Geth client, features which allow us to expose and export all of the state data so that we can index it in the same capacity that we're indexing it for Ethereum. Let's see if this has finished.
I saw you in one of your database tables. I saw a glimpse of Bitcoin in there as well.
Yeah, that's true. That work has kind of been sidelined. But yeah, we have the analogous tools here for Bitcoin, IPLD BTC index or IPLD BT server. For Bitcoin, we can actually do the process in a separate remotely. We can consume the Bitcoin data remotely and index it with this separate process rather than having to write it into the Bitcoin client, because obviously Bitcoin is much much slower and easier to keep up with than Ethereum is. So yeah, we have these tools for generating the BTC IPLD cache and exposing that cache using the conventional interfaces and these additional new interfaces. But that work, as you can see, hasn't been updated for a while, and our focus has really primarily been on Ethereum and now Tendermint and Cosmos. Oops. Sorry, I can't see this completely. Oh, of course. Well, for some reason, the balance is still not reflecting, and I can't really explain why that's happening. You can see it reflected here again. We've got 0.00000, how many zeros? 2 now, but it's not reflecting in the GraphQL server. But what we can see in this other query is the actual transfer event that occurred, and you can see that the value was transferred to this address that we're querying. And additionally, in each of these responses, we have a proof although this is probably more aptly called evidence because it's not a properly formatted Merkle proof. Rather, it's just all of the IPLD data that we would need to construct that Merkle proof.
Right.
And one of the reasons why it's like this right now is because for a lot of the data that we're querying, there's not a single path. There's not a single set of nodes along a path to prove the data. You would actually need to prove the existence of multiple objects. And so we're still trying to figure out how to best represent that in like the most compact form possible and the most conventional form possible. But rather, yeah, right now what we're providing is all of the IPLD data that you would need to construct such a proof, or fetch all this data from some other source and verify it independently.
So this is the kind of thing that you could use to build bridges, for instance, between two chains.
Yeah, absolutely. What it allows us to, index the essentially arbitrary blockchain data from any blockchain source in the same IPLD format, which allows us to use the same interfaces, the same tooling to query that data and generate proofs for all of that data. So that's sort of the high level goal, is empowering developers and people to query data from arbitrary blockchains in the same capacity and generate cross-chain proofs. And
Yeah, and then of course, IPLD, IPFS data is self-verifying. You've got that, and then you could compare that, and multiple people could be hosting it. In basically, it's a data availability solution.
Exactly, and one of the high level what Vulcanize is working at is a protocol that provides that functionality, and I don't think I'll get into that today. I'd have to let Rick speak on that further at some time. But that's the ultimate goal for Vulcanize, is to create this protocol, this new network, which will actually be based on Cosmos, or it will use the Cosmos SDK to improve data availability for Ethereum and other blockchains, and provide a uniform interface for accessing that data and proving that data.
So basically, instead of having to run, centralized databases for things like this, different people could run it for different queries and other things like that. Obviously, part of the stuff we dug into things like the transaction API for Filecoin, that's a centralized host that has a big database behind it. So this could be applied to any blockchain state data. Basically, if you write the appropriate indexers and IPLD codecs.
Exactly. And that's precisely what we're working on. And I'm not sure what the next blockchain will be that we approach, but I think it'd be really cool to extend this functionality to Filecoin. And I don't know if there's any, if maybe you could speak on the interest in that, or how you could see this being used in that capacity.
I'm just generally just trying to promote the fact that this is possible.
Yeah.
And everything from things like GraphQL that makes it applicable to front-end developers much more easily, as well as making complicated queries and caching queries and all of this other good stuff, where we're leaning into IPFS and IPLT. So obviously, to me, that just makes sense that Filecoin, which is so intertwined with IPFS and IPLD, could make use of this tool chain as well.
Yeah, absolutely. And as I understand it, Filecoin actually uses the DAG PD codex, or sorry, is it the DAG Seaboard codex for most of its data? And so we wouldn't actually have to write any new IPLD codecs for that data. We would just have to write, this data pipeline that indexes and exposes that data in this same capacity.
Carson and why, is this giving you some ideas of how this could be used for some interesting cross-chain stuff?
Yeah, absolutely. I think
I was talking to Carson and YC. I know they're muted,
sorry.
but and this is a lot to drop on this early in the morning, but this is kind of the stuff that I wanted to make sure that Ian could show that's possible.
Yeah, this makes a lot of sense. Been thinking about this approach for a while. I don't know. I feel like I'd love to play around with it and see what it can do. But yeah, this is a really effective way of getting like nice Merkle proofs for whatever.
Yeah, I think that's the interesting thing. It's literally the like, whatever do you want to prove? And Carson, I wanted to put this on your guys' radar as you think about cross-blockchain stuff. This is all brand new, but ideally some really interesting building blocks, especially if Filecoin is the target to prove that you've stored some data or made it available on IPFS. This seems like a really powerful toolkit for that, instead of having to write a bunch more stuff from scratch. And Ian, I assume this is all kind of open source based and available for people to work with?
Yeah, absolutely. I think the only repo that's currently private and will be made public shortly is this ERC20, this demo repo. But all of the components that are being used in that repository are all open sourced, and most of our stuff is licensed under AGPL. The work that we've been doing in conjunction with IPLD, the codec work, that's licensed under dual MIT and Apache licenses to match the licensing scheme that they're using for all the other codecs that they've written. But yes, all this work is open source or will be made open source.
Great. What do you want help with? What do you want people to try?
That's a good question. I think it would be helpful for people to try. Well, it would be helpful for people to try running the indexing stack from the bottom up. To generate, it's a lot to ask, but to generate these gigantic low-level IPLD caches. And I think if you start at that level, that's where you'll get the most. You can build out the most features. You can do whatever you want with this IPLD data. But that is a lot to ask because it is a rather expensive process to run, or at least on the mainnet. You could run this on your own test net or Rinkeby. Well, actually, Rinkeby would be really expensive to run it on too. But yeah, you could run this on a test net and get a feel for things, and it wouldn't be too intensive. But then at a higher level, I think it would be useful for people to try out the Watcher TS to create their own. This is more from like a consumer perspective, to create their own watchers that consume this ETH IPLD data and transform it and index in some capacity that's useful to them. Obviously we can't predict what format everybody's going to want to end up converting this Ethereum IPLD data into. So it would be useful. It provides insight into like what low-level indexes we should be exposing. If people come at it from this level and figure out how they're actually consuming that data, how they're actually searching that data, and what additional transformations they need to apply on top of it. Potentially we can go and modify the low-level cache based on how people are consuming this data and using this data. If there's some index that we don't have at that level that would be useful to people, then we could add it. But yeah, we can't really predict exactly how this data will be consumed from an end user perspective.
So Peter has a question. So when you say gigantic, how large are we talking for Ethereum mainnet?
That's a good question. So right now in our production database, which is not entirely complete, we have about 8 billion IPLD blocks. And I don't know if I can get you like a gigabyte size, or it'd be terabyte size. yeah, I don't have like a byte size for you, but that I think gives a good idea of how large this actually how large this database ends up growing into for a mainnet blockchain.
Is that effectively archival?
Yeah, it is archival. Yeah.
Nice.
Yeah, archival in a way that can easily be queried.
Right. So it's even larger than a normal archival node. Obviously, the Go Ethereum client is focused on one specific thing, which is consensus, maintaining consensus and building consensus. So they don't have all these excessive indexes from their perspective in their databases. So the data is even larger when it's expanded out in this capacity.
I think the interesting thing is really, if you want this type of functionality, you have to have somebody run these things. And right now what we have is we have multiple people doing this because the way that, because they're not using IPFS and IPLD, so you can't, you've got database data, not verifiable data with proofs in it. And I think that's the interesting thing, is that different people could care about different things and share and verify the proofs, right? Which is what's interesting about this approach.
Right. And with this, sorry, I keep moving to the wrong tab. With this Watcher TS package, these are more specific transformers. These perform more specific transformations on that low level cache, but they also cache the IPLD data. So the new format, the new output of these transformations is still provable using the IPLD format. But so it allows people to write more specific, to generate data formats that are more useful to their specific use case while still being able to prove it in the same capacity using the IPLD data format.
Yeah. Do you have a test instance running somewhere that people can write these watchers against, or where are those?
That's a good question. Actually, I don't know if I have an answer for that myself. I mean, obviously this production database is not open to the public, but Vulcanize would be, if you approach Vulcanize and you want access to this database, I'm fairly certain we can give you read access to this database so that you could actually begin querying the mainnet data. Otherwise, and we actually do have Rinkeby as well, although currently that server is not stood up. But otherwise, the best way to play around with it would be to instantiate your own local testnet, not like your own testnet, not Rinkeby or one of these other public testnets, but a private testnet that doesn't have all of this, doesn't have so much data in it. Although, I mean, one of the problems that we really run into building out these systems is that you can't really properly test them unless you're testing them on data that is representative of the complexity of, it was representative of the complexity as you see it on mainnet. So it is difficult to get a feel for things testing them on a private testnet where you don't have billions of records that you need to query. So we do end up. Oh, sorry,
interesting to think about. I think in general, I think that and depending on what else happens with other networks becoming available and so on, then different ways to make it so people can stand things up more easily would be something to look at.
Yeah, absolutely. And I can revisit that after giving it some more thought. I'm sure there's probably some tools that I'm forgetting to mention. There's a lot of different utils that we've built out, and yeah, some other tools used for building out those test environments, but I can't recall it all currently.
No worries. I know this is a big system, and I wanted to at least give people a taste of some of the basics. Peter has another question. Have you considered OpenPG replicating your main database? Make an internal replica, chain a public repo off of that, provide a seed start to dump from via IPFS or Filecoin, and then folks can chain replicate if interested.
No, I don't think I have thought of that. That's a really good idea. I'll have to look
Okay.
into that more.
I think Rick just dialed in and said, "Yep."
Okay. Well, he's thought of it. I haven't.
We'll for everyone on the call, Ian's going to put links to things in the Filecoin repo, and everybody who's put their email in, we'll send follow up so that you can connect to Rick and Mally and the team to dig in further if you're interested. Other questions? Yeah, I know this is a lot to digest, and thank you for joining us early West Coast time. It was, I really wanted to have Ian walk through so we can get a sense of what this looks like today. Again, like I said, to make sure that people realize that this was a toolkit that was available, and rather than needing to replicate or work workarounds, that this is something to analyze to see if it meets some use cases that you have. Carson, like you said, inclusion proofs, transaction APIs, whatever we might possibly throw this at on in Filecoin land as well. Amazing. So I have a recording. I will hit the. I'm on